Hello. In this video we will begin to consider the spectrum of a bounded linear operator. As we will see, the spectral theory of bounded linear operators generalizes the investigation of eigenvalues and eigenvectors of square matrices, but because of the more general setting, the structure of the spectrum and the theoretical results involved turn out to be quite rich compared to the corresponding concepts for matrices. Throughout the chapter, we consider a complete normed space X and let T be a bounded linear operator from the space X to itself. The definitions of the resolvent set and the spectrum of the operator T both involve the bounded linear operator lambda I minus t, where I denotes the identity operator on the space X. The resolvent set of T is defined as the set of those complex values lambda for which this operator lambda I minus t has a bounded inverse. And by this we mean that the inverse is defined as the mapping from the whole space X, and the inverse is bounded. By the bounded inverse theorem, this property is equivalent with the operator lambda I minus t being both injective and surjective. And in addition, we define the spectrum of T as the complement of the resolvent set of T, consisting of those points for which the operator lambda I minus t is not boundedly invertible, or equivalently lambda I minus t is either not injective or not surjective, or both. As in the case of eigenvalues and eigenvectors of a matrix, the spectrum of an operator will often tell us a lot about the properties of the operator itself. Before going into very deep into such results, we can also note that the resolvent set of T consists of precisely those points lambda for which the operator equation shown here has a well-defined and unique solution for all right-hand side vectors y. In addition, the solution depends continuously on the vector y, meaning that a small change in y will create a relatively small change in the solution x. And such equations are called well-posed. A wide variety of different types of linear equations can be formulated as operator equations, and especially the functional analytic framework is used to investigate the well-posedness of ordinary and partial differential equations and integral equations, all with suitable choices of differential or integral operators and the underlying vector space X. One particular way that the operator lambda I minus t can fail to have a bounded inverse is that it is not injective. By definition, this means that there exists a non-zero vector x such that the image of this x under the mapping lambda I minus t is equal to 0. And alternatively, this condition can be expressed as the image of x under t being mapped to the scalar multiple of the vector x. And from this last form, it is quite immediate that the concept of the spectrum of a linear operator indeed generalizes the concept of eigenvalues of a square matrix. And the same terminology of eigenvalues and eigenvectors is still used in the operator case for the complex values lambda and for the non-zero vector x, satisfying this last condition. But as already mentioned, the spectrum of a linear operator can in general have more complicated structure than the set of eigenvalues of a matrix. And in particular, an operator may have an uncountably infinite number of eigenvalues, and some operators do not have eigenvalues or eigenvectors at all. And as just mentioned, the spectrum of a linear operator can consist of more than just eigenvalues. The spectrum can be divided into the three parts shown here. And before going into the details, it's worth noting that this is not the only way that such a subdivision can be made. And in the literature, you can also find definitions of other spectral subsets with different properties. But sticking to the division that we have, the first part of the spectrum, the point spectrum, we already encountered, and it consists of the eigenvalues of the operator t, meaning those values lambda for which lambda I minus t is not injective. And in addition to the lack of injectivity, the operator lambda I minus t can fail to be boundedly invertible if it is not surjective. And the remaining part of the spectrum consists of those lambda for which the injectivity holds, but the surjectivity fails. And it is divided into two parts. The first part, the residual spectrum, consists of those lambda for which the injectivity holds, but for which the range of lambda I minus t is not dense in X, and therefore the operator is not surjective. The final part, the continuous spectrum, consists of those lambda for which lambda I minus t is again injective, and its range is dense in X, but the operator is still not surjective. And as we see, the point spectrum contains those points lambda for which lambda I minus t is not injective, and the other two parts contain those lambda for which injectivity holds but surjectivity fails. And the division to the last two spectral subsets is then made based on whether or not the range of lambda I minus t is dense in X or not. The definitions of the point spectrum, the residual spectrum, and the continuous spectrum imply quite immediately that these sets are pairwise disjoint, meaning that any point lambda can belong to at most one of these sets. And in addition, the definitions also show that the union of these sets contains all lambda for which lambda I minus t is either not injective or not surjective, and therefore the bounded inverse theorem implies that these three parts indeed do cover the whole spectrum of t. And even though the definitions of the parts of the spectrum may seem complicated, finding out if a given complex number lambda belongs to one of these sets or the resolvent set can be done in quite a systematic manner, following this convenient diagram from the book by Naylor and Sell. If we begin with an arbitrary lambda, we can first check if the operator lambda I minus t is injective. If the answer is no, then lambda is an eigenvalue of t and thus belongs to the point spectrum of t. On the other hand, if lambda I minus t is injective, we can check if the range of lambda I minus t is dense in the space X. If the answer is no, then by definition lambda belongs to the residual spectrum of T. Alternatively, if the range is dense in X, we can check whether or not the operator lambda I minus T is really surjective. And if the answer is no, then by definition lambda is in the continuous spectrum of T. On the other hand, if lambda I minus T is really surjective, then this operator is both injective and surjective, and thus boundedly invertible by the bounded inverse theorem. Because of this, by definition lambda belongs to the resolvent set of T. As our first example, we can consider a multiplication operator on the sequence space LP. And this operator is defined by taking a fixed bounded sequence of elements lambda k and defining T such that it operates on the element x by multiplying its kth element with the value lambda k. Because in the case of finite vectors, this same effect is produced by multiplication of a vector x with a diagonal matrix from the left, we can think of T as an infinite dimensional diagonal matrix. And in this interpretation, the values lambda k are the diagonal elements of the matrix. The spectral analysis of this operator is done in detail in the lecture notes, and here we'll just present a very brief summary. Similarly as in the case of matrices, every one of these diagonal elements of T turns out to be an eigenvalue of the operator T. And indeed, the operator lambda I minus T can be non-injective precisely if lambda minus lambda k is 0 for at least one index k, meaning that lambda is equal to one of the values lambda k. And since the sequence of lambda k can be quite general, we can see that as opposed to a finite diagonal matrix, an infinite multiplication operator can have countably many distinct eigenvalues. Moreover, the multiplication operator can also have other spectrum besides eigenvalues. In fact, all the limit points of the set of lambda k's are also in the spectrum of T. We will learn later that the spectrum of an operator is always a closed subset of the complex plane, so it really will contain all of its limit points. But those limit points which are not in the set itself are not eigenvalues, but instead they belong to the continuous spectrum of T. And finally, all of those points which do not belong to the closure of the set of lambda k, meaning that they are not in the set and they are not limit points of the set, belong to the resolvent set of T. And this way we arrive at the complete characterization of the spectrum of T, where the point spectrum consists of the values lambda k, the continuous spectrum consists of the limits of these values, and all other points in the complex plane belong to the resolvent set of T. And in particular, the residual spectrum of T is always empty. Since the sequence of lambda k's was assumed to be bounded, we can see that the resolvent set is always a non-empty set. Moreover, T always has non-empty point spectrum, but on the other hand, the continuous spectrum may be either non-empty or empty based on whether or not the set of lambda k's has limit points which are not in the set itself. The easiest case where the continuous spectrum is empty happens when in the case where all lambda k's have the same value, for example 0 or 1, and in these cases the spectrum of T consists of a single eigenvalue. On the other hand, even though the set of eigenvalues lambda k's is always countable, the continuous spectrum can in fact be an uncountably infinite set. One example of this happens if we choose the sequence of lambda k's to contain all rational points on the real interval from 0 to 1. And in this case, the closure of the set of lambda k's is the whole real interval, and therefore the continuous spectrum of T consists of all irrational points on the interval and is therefore an uncountably infinite set. In proving that a given point is in the continuous spectrum, we can use another and sometimes more practically convenient characterization of this spectral subset. As shown in the theorem here, a complex number lambda belongs to the continuous spectrum of T if and only if the operator lambda I minus T is injective and its range is dense in X, but the algebraic inverse of this operator is not bounded. Since lambda I minus T is assumed to be injective here, this inverse is well defined as a mapping from the range of lambda I minus T to X, and therefore we can indeed investigate its boundedness. As a further alternative condition, we can substitute the condition for the unboundedness of the inverse operator with another precisely equivalent condition. As shown in the corollary, a complex number lambda belongs to the continuous spectrum of T if and only if lambda I minus T is injective and its range is dense in X, and in addition there exists a sequence of elements xk, all having norm equal to 1, such that the images of xk under the mapping lambda I minus T converge to 0 as k goes to infinity. It's a straightforward exercise to show that if lambda I minus T is injective, then the existence of this sequence is indeed equivalent to the unboundedness of the inverse of lambda I minus T. Especially this second characterization is quite useful in studying continuous spectrum of concrete operators, and in the literature the sequence of xk's is often referred to as an approximate eigenvector of the operator T corresponding to the spectral value lambda. And we can use these results for our multiplication operator on LP if we want to prove that all limit points of the set of lambda k's which are not in the set itself belong to the continuous spectrum. To do this, we can begin with such a limit point and first prove that lambda I minus T is injective, which we already saw before, and that the range of this operator is dense in X. Here we will only focus on the last part, where we show that the inverse of lambda I minus T is unbounded by constructing an approximate eigenvector. Since lambda is a limit point of the set of lambda k's, we can find a subsequence of the values lambda k indexed with n, which converges to the value lambda as n goes to infinity. And for every n, we can now define xn so that it is the sequence whose knth element is equal to 1 and whose all other elements are equal to 0. If we do this, then clearly the norm of xn is equal to 1 for all n, and for every n, the image of xn under the operator lambda I minus t is a sequence whose knth element is equal to the difference lambda minus lambda kn, and all other elements are equal to 0. And this is directly based on the definition of xn as a sequence with only one non-zero element. And because lambda kn converge to lambda as n goes to infinity, the norm of lambda I minus t xn goes to 0 as n goes to infinity. And this concludes that the sequence of xn's is indeed an approximate eigenvector of t, and our previous results imply that lambda is in the continuous spectrum of t.